Okay. Now the streaming has started already. So, ladies and gentlemen, let's start. Come in. Welcome all to my talk about Valgrind register allocator overhaul. My name is Ivo Reiser, and I'd like to first introduce myself. I'm almost 30 years old. I've got some family. I'm from the Czech Republic, which is renowned by drinking beer. I'm an exception. I don't drink any. And I drink wine as well, but there are many Czechs who drink a lot of beer. I like new toolchain hacking. I contributed to many parts of Valgrind, and my hobbies are steam engines, hiking, and playing with my kids. So, why we needed a new register allocator? Huh?
You can't see the entire screen.
Ah, that's very unfortunate. Yep. Yeah, I guess so. Still not so good. I will resize my browser. But this part is visible. It's quite strange. So let's stretch it a bit down. Okay. So let's do it this way. So last year I started adding if-then-else support into the Valgrind immediate representation. It's a big project, and it touches all the parts of Valgrind. And when it came finally to Vex register allocator, Julian decided that it's too heavy, it's too complex to plug the new support in. So the need arises to register allocator v3, which has been merged to Valgrind master. Is it readable at all? Yeah. Okay. So this is my crude picture of Valgrind architecture. This is Vex subsystem, which takes care of keeping the guest state and translating from native code to immediate representation and back to native code. Then there is CoreGrind subsystem, which is actually a VM, and then there are analysis tools on top of this. And my talk will focus on Vex subsystem. So Vex operation, very briefly, still not perfect. Okay. So we start with native code. I showed just one instruction in AMD64, but Vex operates on whole chunks of instructions called basic blocks. So we start with instructions, translate them to immediate representation, then we optimize, instrument them, optimize again, repeat, rinse, and what we get is an IR in a form which is suitable to be translated back to the native code. So we invoke selector, and we get a V code. It resembles quite a lot the native machine code, but it has virtual registers instead of the real ones. So that's where the register allocator comes into play. The allocator registers produce R code, and we are done. We emit the assembly and we are done. Almost. So the VEX register allocator, as I said, operates on whole chunks of instructions, takes V code and produces R code. It's not a one-to-one mapping because we have many instructions which we do not want to appear in the resulting R code, and the register allocator is supposed to optimize as well. Some terminology. Here we have instruction which loads some piece of guest state into virtual registers. These get allocated on go basis. This is an instruction which just moves from one virtual register to another one. We would like to eventually get rid of such instructions. Another normal instruction operating on VREX, and then we can have also calling helper calls. In this case, with 0 input arguments. Another case would be if with 2 input arguments stored in RDI and RSI. There are 4 main passes of the register allocator. The first pass is to scan all the instructions and take note of all the VREX and real regs used by all the instructions. Then we establish a move coalescing chain. In practice, the coalescing chains could be quite long. For one basic block, 10 or 20 elements is not uncommon. Then we establish spill slots. Every VREG has to have a spill slot. And finally, in the final pass, we process instructions one by one, establish mappings between VREGs and real regs, and emit the final code. There are 2 important pieces of reg alloc state. One is VREG state. For every VREG, we keep track of when the VREG comes live. This is the instruction number, and when it dies. So it defines the life range. Then we keep track of real reg, which is assigned to. It can be unassigned. It means it's not live yet or it's dead. And then we have a spill slot, which is a special place in guest state. We also keep track of move coalescing chains. And the other important piece of reg alloc state is Reg state. It's a backwards map from real registers to virtual registers. We also need to have Reg universe. It's a list of all the real registers available to the allocator. In this case, for 64-bit integer class. So, what happens if the reg alloc goes from V code to R code for this simple instruction? This VREG is now coming live. So we establish a mapping. We choose VREG R10, and that's it. For another instruction, better. For another instruction, we take a note about another mapping and use the already established mapping for VR68. It's no rocket science. Interesting part is when we are going to call something. So for the whole duration of preparing the input arguments and calling this function, we need to reserve the call safe real registers. So we need to take note about it. Now, what happens if we are in the middle of the processing and all the real registers are taken? It can happen quite easily. So we have no other choice than spill a VREC. In this case, VREC was assigned to VREC 70 was assigned to R9. So we spill VREC 70 to its spill slot, free the VREC R9, and we are then free to use it for VR15. Come in. This is the list of optimizations put into the recalog v3. These are simple ones, nothing very complicated because it needs to be fast. And they basically come from very simple observations. So we established move VREC collection chain, so we can get rid of some rec moves instructions in the V code. We can reuse spill slots. If one VREC dies, then we can reuse its spill slot for another VREC which comes with. So we don't have to have a unique spill slot for every VREC. We have very simple VREC spilling criteria. We just scan forward in the incoming instruction stream and spill the VREC which is most farthest in the instruction stream. So it means we'll spill a VREC which appears maybe in 15th instruction instead of the second one. We can also avoid spilling if the VREC has been spilled and reloaded and the value in the real register has not changed. For real registration allocation strategy, okay. Oh, I'm going to ask about that, but if you're going to talk, I'm going to talk about them now. I didn't say that. For the list of these real registers for 64-bit integer class, they are sorted according to their preferred allocation strategy. So it means we take the last ones first, and that's because these are color safe. So the observation was very simple. Let's use the color safe real recs for short-lived VRECs because that would be quite efficient. And let's take the color safe registers for the VRECs which span across the function calls. So if we take, for example, R15, then we don't have to spill it before calling a function. And this optimization comes from an observation that on AMD64 it's possible, and x86 is possible to combine several instructions together. So let's assume that VREC is spilled and we have this vcode instruction. So in standard way, we would need to have first reload it from its spill slot to a real register, and then do standard way.
So this add queue instruction doesn't really exist like that. What do you mean?
No, it doesn't. It doesn't, but it's just for an illustration. So we can directly load it from its spill slot. Several benchmarks have been made on different platforms. I made benchmarks on ARM64, PowerPC S390X, and MD64. Here, just one of them is shown. It's with running memcheck on perf bzip2, and we count the total number of instructions. So this is total number of instructions for memcheck, which is running this this test. So the register allocator v2 No, it's total. It's total. It's total for the memcheck, for the whole memcheck running this test. So v3 is slightly better. If we take just the register allocator itself from this total, then also v3 is slightly better, and that's very good because it's simple. Much simpler than the V2. And if we look at the ratio indicates how much code bloat was introduced by all the translations and instrumentations and allocations. So if we take one instruction on the input and then we translate it, instrument it, and translate it back, we get on average 16 instructions output. So yes, it's all in memcheck. So v3 outputs a slightly better code, which is quite good because it helps with iCache misses.
So you should say also this actually understates the improvement is much bigger than this, because mathematical instructions in memcheck are in the total functions, which you don't make any difference for. So the actual bit generator is much better.
Right. That's true. That's true. But I didn't measure the improvements made by just the alloc itself.
Yeah.
So the new version v3 is now in the master, and it will be the default one with the next Valgrind release. Is it? No, it was integrated in August. I checked, I think. Or maybe some optimizations went later. And the default implementation is still available. So if anyone wants to play with the old version, it's still there. And that's it. We would like to hear your opinions on how to improve the allocation strategies better. If you have any ideas, suggestions, please let us know. All the optimizations are just simple ones, so based on simple observations. Compilers have much sophisticated ones. Okay, so now I'll take any questions. We've got 5 minutes.
Can you ever zoom enough to start allocating the argument registers for
Do you mean in this in this allocation strategy?
I mean, starting allocating the register for the call instructions when you have one in your string. In your previous example, you mentioned we have the call instruction and we might use RSI here.
Okay.
Any reason why not starting with the call and allocate around it and still not potentially not as much?
But even you would start at the call instruction and then work backwards.
Yep.
But there are many call instructions, so where would you start?
It's the first one.
Okay, I see. Yeah, it would be more fun to explore. Why not? I don't know. It needs to be tried. Anyone else? Okay, if not, then we are done. Thank you. Nice call. Ah, thank you. So, if you would like to see all the yeah, and especially because
Check it out, check it out. Oh, very good. Yes.
Thank you. Please, I need to give you instructions how to operate. Especially turn your belt or pocket.
Can I use your laser pointer,
Okay.
please?
And flip it maybe here.
Here? Or like this?
Somewhere here, maybe here. Up to. So it's free.
Oh shit. Testing.
We cannot do anything.
1, 2, 3.
And then we are done.
I think so.
Perfect, okay.
Yeah, but still, can I borrow your laser pointer, please? I hear these are very good for cats as well. You're playing with cats.
No idea.
You have no cats?
No.
Because you can do this and the cat will run after it.
It's enough.
They run after it.
You want some indications? No?
So I think it's from 11:30 until 12:10. Is that right? So I don't actually have that many slides.
11:30, 12.
Yeah, I try. Well, you can you can throw something at me if it's. I have only 14 slides anyway.
5 minutes, 10 minutes.